Hello, my name is John Levesque. I am the Director of Cray's Supercomputing Center of Excellence, and I'm also in the CTO office. I have a website listed here. What I am going to be doing is giving you a series of 6 videos. These 6 videos will discuss the PerfTools Lite suite of experiments. These experiments are particularly designed to be very easy to use. The PerfTools Lite suite includes PerfTools Lite, which gives you a summary of MPI, compute, memory, I/O, and power. PerfTools Lite Loops gives you loop iteration counts for all of the loops that are executed in the program. PerfTools Lite HBM gives you array utilization in the program, in particular identification of those arrays that utilize most of the bandwidth. The first video will cover using PerfTools Lite. We need to load 2 modules, PerfTools Base and PerfTools Lite, and then make the application as usual. You then run the application as usual, and then we will look at the output. The application we will be looking at is a relatively small astrophysics code developed at North Carolina State University. It is an excellent training application because it really has a lot of very interesting features that can be optimized, and we'll be looking at a lot of those in these 6 videos. So the very first thing we are going to do is make the application. There's a nice make file. Notice that the Fortran option HList equal A is being used in this make file. That gives us an annotated compiler listing of the Fortran routines, and this is going to be extremely important when we start analyzing, relaying the PerfTools Lite statistics to the main program in the second video. So it tells us here at the end of the build that after the build that PerfTools Lite instrumented the executable, and it's a sampling instrumentation, and the sample rate is 1 sample every 100th of a second, which is pretty reasonable. Now we are going to submit the job. We have a run script called run it, and we are going to run on 512 MPI tasks across 16 nodes. Each MPI task, or excuse me, each node will have 32 MPI tasks on it. Now this S basically says to put 16 MPI tasks on each socket. That way we can even out the utilization of the memory bandwidth. Okay, now we're going to submit the run. And we are going to be running this on Broadwell nodes that have 36 cores on each node. So the situation here is that we are only going to be using 32 of the 36 cores. Now this is going to take about 2.5 minutes to run. We're going to run at 100 time steps. We'll get a small amount of output from the job itself. And then we'll get the statistics, the Perf Tools Lite statistics, added on to the end of the output. So this output directory is actually the restart files from the application. This directory with the S on the end of it is where Perf Tools Lite is putting its statistics. Now when the program is finished, we will see a output file from the program execution. So we'll have to keep on looking at this. One thing you might notice during this, I do not have a recording studio, so you might notice a couple emails come through, or you might hear a cat meow or a dog bark or a garage door open. My office is above the garage, and so there'll be some disruptions, but hopefully they won't be very severe. Yeah, it's still, let's see, we can do a Q stat. And we're still running here. Okay. I thought it was 2.5 minutes. I'm sure it'll be done pretty quick. Okay, here we go. So we can see here we have an output file. So let's edit that. All right, now one thing I need to warn you about. I'm redoing many of these videos to adhere to a new version 7 that really is brand new, and hopefully by the time you see this video you will have that version. So these are printouts from the program's execution. This is running 100 time steps. And you can see that actually it ran 3 minutes. Then we have the Cray Lite performance statistics. Here again, this is version 7. So if you're looking at a version 6 output, some of this will be different. So it gives us the number of MPI ranks, the number of PEs per node, on 16 nodes, the number of threads per PE. We are not doing any OpenMP in this application. It's all MPI. And this is the number of cores per socket. Now there are 2 sockets. So as I said earlier, there really are 36 cores, but we're only using 32 of them. This is when the execution time started. This is the clock cycle rate of the machine. It's a Broadwell and running at 2.1 gigahertz. This is the average process time. Now all of these statistics are averaged across 512 MPI ranks. Now we will be getting some load imbalance information, which will tell us if there is imbalance between the MPI ranks. Okay, now this is the high memory. This is the total amount of memory used by all 512 MPI tasks. And this is the amount of memory per MPI. But remember, there are 32 MPI tasks on each node. So this is using over a gigabyte. This is interesting. This is a percent of cycles stalled. What this is saying is that there's half the time is spent waiting for something. Now that waiting is usually waiting for memory accesses. Also, the vector intensity is very low. It's 5.5%. So we don't have very good vectorization, and we appear that we could be memory bandwidth limited. This is the I/O read rate and the I/O write rate. Now, the first table we run into is the profile by function. These are the sample percentages. Notice that MPI is actually using more than the user code. And most of that MPI is spent in MPI all-to-all. And then some is spent in MPI all-reduce. Now, one thing, you notice that there's nothing listed less than 1%. And that is the default. If I wanted to see everything, then there is an option that I can use that will give me all the routines, all the MPI calls, even if they use less than 1%. This is the total number of samples. Remember, I said that there was a sample every 100th of a second. So this ran 210 seconds. And MPI took 127 seconds of that. 77 seconds was spent in user routines. Parabola, Riemann, sweep Y, sweep Z. These are all exclusive times. That is the time spent in that routine, excluding everything that it calls. Now the next table is very nice. First, it gives us about the same information on MPI. But for the user routines, it actually gives us the line number in the routine that is using most of the time. Now, the reason why there's only one here is because there's only one line that's using more than 1%. In Riemann, we have 2 lines. And so this, in fact, in our next video, will go to these line numbers and actually investigate whether they're being vectorized, what kind of memory access they're having, etc. And then in sweep Y, we have a couple line numbers, etc. So that gives you, with sampling, you get granularity finer than routine boundaries. All right, let's go down a little more. Now, this is kind of interesting. When we use instrumentation tracing, we can get much better MPI information. But when you sample, we can't get information about whether there's sync time involved, actually, what kind of message passing there is, etc. Now, this is a new table, and this is very nice. Notice that there's 2 NUMA nodes here. This is socket 0 and socket 1. So there are 2 sockets. What this is telling you is that how much of the memory traffic is local versus to the other socket. Now, since this is all MPI, we would expect that, and we have a very nice balance between the MPI tasks across the two sockets, we would expect that a large majority of the total traffic is local. If, on the other hand, we look at an OpenMP code, we would see, and this is extremely important, we would see when threads are actually going to the other socket for memory. And this says thread time, but this is really just MPI task time. And this gives us a memory traffic gigabytes per second. This gives us a little idea about the load imbalance. You can see that this is not really load imbalance with regards to memory. This is one processor, and this is one of these is max and one's min, as it says here. All right, now here is the power. And this gives you min, max, and average memory or energy consumption. And then table 5, these are all our restart files, and it read time, how much data was read, the read rate, bytes per read, etc. And then down below, we have the write statistics. Okay, and last table gives us an idea of the Lustre file information, which OST it was using, the stripe counts, stripe offset, and the size of the stripe. Okay, now we can, in fact, generate other reports from the data. We have this directory I told you about that we can actually do a pat report to get a call tree or callers, etc. I'll show you some of these in future videos. That's it for the first video. I'm sorry it's so long. It did have the introduction in it. I hope you are excited enough to view the other videos.